morning, friends. In continuation to whatever we discussed in the last lecture, if I recall, what are we trying? We are trying to understand a second order system, which is typically mass spring damper system. And we are doing all these things because we are preparing ourselves to understand the dynamics of an airplane when it is disturbed about its equilibrium. We are also very clear we are talking about small disturbance about its equilibrium. And we are trying to build our understanding of a second order system with the presumption that this knowledge will be useful in analyzing the dynamics of an airplane under the influence of small disturbance. We also understand that we are more bothered about transient, and that is the part we need to understand if we want to characterize the dynamic stability of an airplane. And if you recall, when you talk about mass spring damper system, we got equation of this form x double dot plus c by m x dot plus k by m equal to ft. But if it is a free response, this is equal to 0 for free response. And this is what we are looking for, right? We also understood when we try to find its characteristic equation, we realized that depending upon the value of C, M and K in their combination, I could have situations where C is the damping coefficient is less than a particular value, say C less than C critical. Then we said this will be under damped case. If C is greater than C critical, we said it is over damped, and C is equal to C critical. It is the boundary between over damped and under damped case. But we also know one thing, that if the damping coefficient C is chosen such that it is equal to C critical, then the time to return to the equilibrium will be not only non-oscillatory, it will be fastest. You also realize that if it is over damped case, there won't be any oscillation, but it is under damped case, then there will be oscillation, and it will take some time to come back to the equilibrium. In understanding this, we try to define two things which are important, zeta and omega n. And zeta is the damping ratio. It is actually the ratio of actual damping C divided by C critical, right? We recall zeta is C by C critical. So if zeta is less than 1, that means C, the damping of the system is less than C critical, so it will have an under damped response. If zeta is greater than 1, it will have an over damped response, because that time C is greater than C critical. And if C is equal to C critical, then there is a boundary. It will also be non-oscillatory, but it will come back fastest, return fastest to the equilibrium once the disturbance is withdrawn. We are all talking about the disturbances when you are assuming that there are small disturbance about the equilibrium. And so we realize that if this equation, which is equation of motion for a mass spring damper system, that is how its x coordinate is changing, how this gentleman is moving in x direction. So this is the equation of motion, and we realize that if we can transform this equation of motion using zeta and omega n, where omega n is the natural frequency, and we understand natural frequency means the frequency of oscillation if damping is 0. Okay. So in doing that, we came up to a point where it is d square x by dt square plus 2 zeta omega n into dx by dt plus omega n square x is equal to 0. And it goes without saying, when I write x, this means x function of time, this is function of time, this is function of time. This is same equation as the equation given by this for a free response, written into using zeta and omega n. Okay? Now, we'll have a little bit of halt and we'll try to learn the last thing which is required from mathematical background. And then, as I promised you, after this lecture, you are ready for utilizing this understanding for analyzing dynamic stability of airplane. If you see here, we are talking in terms of time domain because x of t, right? This is in time domain. We are also observing that this is a differential equation, right? Now, historically, one of the approaches, why don't we change this equation from time domain to a frequency domain? And that is essentially a Laplace transform. We'll just use the gist of Laplace transform, and whatever I am telling you, if you recall this much, it's good enough for our future analysis, right? Laplace transform of a function is defined as that is f of t is the function. You multiply with e to the power minus st, where x equal to j omega, omega frequency, and integral over 0 to infinity. And you could see it's an improper integral, right? So what is the advantage of this? Let us see. Once I take Laplace transform for a function, let us say the function is f of t equal to 1, right? Then what will happen? Laplace of f of t, which is equal to 1, will be 0 to infinity e to the power minus st, f of t is 1 into dt, right? However, you understand this is improper integral, so we have to follow a procedure. So we'll write integral 0 to a limit. Don't get confused with limit and all such things. Limit a tends to infinity e to the power minus st into dt. And then this will be equal to limit a tends to infinity, and this will be e to the power minus st by s 0 to a, and a tends to infinity. Right? No issues? This again, once I put the limits, I say limit a tends to infinity, this will be minus e to the power minus a s by s plus 1 by s. Right? I put a and 0 to be the limits. So what is happening if I do that? See, understand, this is very important. As long as s is positive, as long as s is greater than 0, if I take this limit, this gentleman will go to 0, and the result will be 1 by s. This is extremely important that s has to be greater than 0, otherwise it will not converge, right? So this is simple trick for finding Laplace transform. For any other function, you can replace ft by that function, do the integral. Sometimes you have to do by parts, and you should be able to get the desired expression. In fact, the Laplace transform for all these standard functions are available, right? You need not do all those functions. You should try one or two. you can refer book by Krzyk, Engineering Mathematics by Krzyk, and in half an hour you can swap through and get the hang of it. So this is to introduce you in Laplace transform. What is happening, you see? The time domain function is being transformed into a frequency domain. That's the important thing. If I stretch this understanding for functions which are derivatives, then you can see that I'm just writing the result. This Laplace of f prime t is s of Laplace of f of t minus f of 0. Similarly, Laplace of f double prime t is s square Laplace of f of t minus s f of 0 minus f prime 0. Again, strongly advise you, you can do this by using the definition of Laplace integral, put them, use integration by parts, you will get these results. Just to make you familiar, suppose I am trying to do for x dot. So as per this, Laplace of x dot will be equal to s Laplace of x of t minus x of 0. So which I write as s x of s minus x of 0. Is this clear? This Laplace of x of t is x of s by notation. Right? Similarly, if I try to find out Laplace of x double dot t, by this I will get s square into Laplace of x of t minus s x of 0 minus x prime evaluated as 0. So this I can again write as s square x of s minus s x of 0 minus x prime 0. Since we are dealing with a linear system, and for linear system, you can always put these initial conditions to be 0 because this will not affect the stability characteristics. If it is nonlinear, then you cannot do that. Since we are talking about linear system, small perturbation, so I can always approximately write Laplace of x double dot t equal to s square x of s Laplace of x dot t is equal to s x of s. Right? Please understand, I have taken these initial conditions to be 0 because as far as stability is concerned for linear system, it doesn't matter what is the initial condition. Right? See the beauty. If I now apply this understanding to that equation, what happens? Let us try to see that. Now, let us revise. Laplace of x double dot will be s square x of s because I am putting all the initial conditions 0. Laplace of x dot t will be s x of s. Clear? So now come here. If I take a Laplace on both sides, so this is x double dot, so it will be s square x of s plus 2 zeta omega n s x of s, because this is x dot, plus omega n square x of s. This is equal to 0. Right? Please understand, this was the characteristic equation assuming free response because I am interested in the transient analysis. This is in time domain, and this is now in frequency domain. Okay? S is basically j omega, so this is in frequency domain. We are all taking advantage of linear system, and this is in time domain. So now, what are the differences you are finding here? Please see here. The moment I take a Laplace transform over this equation, this resulting characteristic equation is an algebraic equation, isn't it? You see, this was the differential equation, and this is algebraic equation. This is the first advantage we got. And that will be our prime advantage for working in the frequency domain or using the Laplace transform. So now what is the characteristic equation? Equation is x of s, if I take common, then it will have s squared plus 2 zeta omega ns plus omega n square equal to 0. Right? So my characteristic equation now becomes x squared plus 2 zeta omega ns plus omega n square equal to 0. Right? Clear? So this is the characteristic equation in frequency domain. Now see how we can use it. Why we have come down to this sort of equation? Because our aim was to find out zeta and omega n of the system. What is the damping ratio? So that I know whether the free response is oscillatory or it is the critical damping, or it is over damping, or it is under damping. And also I need to know what is the natural frequency, that is the frequency of oscillation when damping is 0. And if I know this, I can easily find out what is a pseudo damped frequency, which derivation we have already made. These are our purpose, right? Now how to use this equation, that is the question. Let us take a mass spring damper system, and which is x double dot plus c by m x dot plus omega n or k by m is equal to 0. This is my mass spring damper system. Now I want to find out what is the value of zeta and what is the value of natural frequency. What I do, I take Laplace transform, so I get s square x of s plus c by m s x of s plus k by m x of s equal to 0. Right? I have just taken Laplace transform here. I know for x double dot it is s square x of s. For x dot it is sx of s. For x it is x of s. So if I take x of s common, I have s square plus c by m s plus k by m equal to 0. So what is my characteristic equation? It is s square plus c by m s plus k by m equal to 0. Now I want to find out what is the expression for zeta and omega n for the second order system. We are very comfortable now. We know that for second order system, the characteristic equation can be also written in this form, that is x squared plus 2 zeta omega ns plus omega n square equal to 0. So I can map this and find out what is the value of omega n and zeta. If I compare this, I get omega n square equal to k by m and 2 zeta omega n equal to c by m. I'm just comparing this two equations. S square, 2 zeta omega n is nothing but c by m. Then k by m is nothing but omega n square. So what does this tell you? The natural frequency is under root k by m, and zeta will be equal to c by 2m, right, into 1 by under root k by m. See, zeta will be equal to c by 2m, here by omega n is k. That is, if I know the value of spring constant k for the spring, if I know what is the mass of the spring, I will be able to get the value of zeta and natural frequency. Is this clear? So that is how it is very handy. Is this clear? Okay. We will be solving few examples, and you realize it is also important to know whether the system will be oscillatory or it will be just without any oscillation come back to the equilibrium. all those finer details we will see as we progress, right? Okay.